So of course I'd like to thank the organizers. It's been an absolutely fantastic and refreshing conference with just an absolute amazing array of talks. In particular, I think Dr. Nicole Salazar's talk, retention, is sorely needed, and I'd just like to thank them and thank also especially Raquel and Brandon for the Astronomy on Tap last night, which was so much fun. So although my name is Dr. Coral Wheeler, I think from now on, I'm going to start going as the Scarlet Satellite. And I don't know if you can see, but I look pretty good in that cape.
How many people were there?
300. It was fantastic. Fantastic. Okay. So this is my first review talk, and also the first time I'm giving the last talk, so we'll see how that goes. And I kind of wish I did more of like the personal history of everyone involved, but I'm just going to kind of set the stage theoretically and take it from there. Okay, so our best sort of accepted cosmological model, Lambda CDM, according to that, cosmic perturbations are imprinted on all scales in the early universe through quantum fluctuations and inflation. Later, when the light redshifts away, these become mass perturbations, and they grow linearly at first, and they collapse further through their own gravitational instability in expanding universe. Now, initially, it's only non-baryonic dark matter with no pressure that can participate in this collapse, and these objects eventually pull away from the Hubble flow and form virialized dark matter halos, and that's what you see here. This is a dark matter only simulation of a dark matter halo that will eventually, we expect, host something like the Milky Way. So before we had simulations, if we wanted to then take these early conditions and figure out what does that mean for today, we had to use some fancy stuff, pressure sector formalism, extended pressure sector, but the basic idea was if you make the simple assumption that your dark matter halo collapses sort of like a spherical top hat, and then you extrapolate the linear growth into the nonlinear regime, you can get the co-moving number density of these halos, both as a function of halo mass here and as a function of redshift. Well, now we have huge, massive dark matter only cosmological simulations, much larger scales than the one I just showed you, and they pretty much agree. They get it pretty close. We think we trust these a little bit more, but both of these were used, and they give us basically the mass function of halos. So that's one piece of the puzzle. Now we need the galaxies. So with the advent of big surveys like Sloan here, which is mapped, I think, a third of the sky, we also now can get co-moving number density of galaxies. We can get a galaxy mass function. And with those two pieces, if we line them up side by side, we can match those co-moving number densities between halos and galaxies and start to learn about the relationship between the observable matter that we see in the universe and the dark matter that we see in our simulations. So here is, I see it. I'm going to use this one. Is that better? Yeah, okay, here we go. So here is the halo mass function, and this dashed line would be what the galaxy mass function would look like if every galaxy turns its cosmologically allotted fraction of baryons into stars. But it doesn't do that. This is the actual observed function of galaxies, and we can see that even at the peak of efficiency of star formation, even right here, what we call an L-star galaxy, these, which is similar to right around the mass of the Milky Way, we can see that it's not turning even its cosmologically allotted baryon fraction into stars. In fact, it's a tiny fraction. So I think it was Juna Kohlmeier who said, you wouldn't hire the Milky Way to turn gas into stars. But if you consider the rest of the field, it's still going to be your best bet. Because when you move to higher and lower masses, you can see that the galaxy formation efficiency is even less. So here at the high mass end, not all of that gas cools. You also have AGN feedback preventing collapse. And at the low end, we think it's the supernova explosions feedback from supernova. Okay, so when you match these things, then you can get a relationship between the stellar mass and the halo mass. And if you do this this combined with basically Lambda CDM and that theory, it gets a lot of things right. It's surprisingly correct on the biggest scales. I'll just flash them up. We talked about the CMB, the clustering of structures over 10 decades in mass. It gets right from Milky Ways all the way up to superclusters. The acoustic oscillations imprinted on the matter-power spectrum at recombination. The bullet cluster. Someone asked me last night about some alternative gravity theory that I wasn't really that familiar with. At Astro on Tap. And I just said, look at the bullet cluster. I didn't know what the answer was, but it's a, it's a good place to start. So, and then actually, usually I just go ahead and put the answer up for these talks, but I had so much fun making people guess. But for those of you that were there last night, this is different, maybe. So one of these is the real distribution of galaxies from Sloan. One of these is basically a Bolshoi cosmological simulation where we used that abundance matching technique, putting the biggest galaxy in the biggest halo to make a mock observation of the universe. So, all right, show of hands. Right side. What's the real universe? Sloan. Right side? Left side? All right. Yes, the blues have it. The problem is I haven't figured out how to change the red to blue and the blue to red. So even if I switch the sides up like I did this time, those of you who might be able to remember, but they're statistically indistinguishable, right? We're doing a really good job, or Lambda CDM, but Lambda CDM does a fantastic job on the biggest scales. But I'm not here to be a cheerleader for Lambda CDM. I'm here to talk about some of the small scale challenges. So it gets a little bit more interesting when you start to look at the small scale. So this is another dark matter only simulation. This time we've zoomed in on a Milky Way mass halo. And Lambda CDM still predicts that a Milky Way has thousands and thousands of these tiny smaller subhalos orbiting in and around it. But of course, when we look out, we actually see only on the order of tens. I mean, more and more every day it seems, but still, there's something going on. There's a mismatch. So that's the first challenge I'll be talking about today. Also on small scales, Lambda CDM predicts, at least according to dark matter only simulations, that all of these halos have a universal mass profile. This was first sort of described by Navarro, Frank, and White, and it's named after them. It's the NFW profile. It has a log slope of -3, and it rises to what we call a cusp of a log slope of -1. However, things aren't always so clean when you start to look at real galaxies. In fact, usually they're not. And it was discovered that at least for some lower mass galaxies, if you now look at that slope, that log slope I told you about, it's supposed to end at -1 here, like the NFW profile. We actually see that it actually is much flatter. It has a flat density profile, a slope of 0, or what we call a core. So this is the second challenge I'll be talking about. And then finally, I'm going to spend a little bit of time discussing, I guess, a tension between the diversity of density profiles or rotation curves. I guess that's how it was kind of described by Oman et al. And they looked at a bunch of dwarf galaxies, and this is now rotation velocity. But you can see here, you both get a less steep rising velocity curve, or sometimes you even get more steep. It's super diverse. And then if you contrast that to the remarkable regularity of the galactic scaling relations, such as baryonic Tully-Fisher, I think it's an interesting tension to consider. So this is baryonic Tully-Fisher, where the flat portion of that rotation curve of galaxies is found to be proportional to the baryonic mass to the 4th power. If you just use stellar mass, the lower mass galaxies kind of fall off. And this is interesting because you might think it's feedback or something that is keeping these galaxies on this relation. So it's even more interesting that's related to baryonic mass rather than stellar mass. Okay, so that's the third kind of tension or challenge. So one might say Lambda CDM is at a crossroads. So far, it's done a pretty fantastic job on many scales. A surprising job, especially when placed up against some of its more competitors. But we still don't have a dark matter particle candidate, and small scale challenges just seem to be popping up faster than we can explain them away. In fact, there are many more challenges that I'm not going to be able to get into today. So I'm going to talk about some solutions, and although I guess I promised I wouldn't be much of a cheerleader, I am going to stick within the confines of Lambda CDM, although there are many potential alternative theories both that are Lambda CDM, such as adding a self-interaction term to the dark matter, both that are similar, like a warm dark matter. It's a wealth of other issues, but I'm going to focus on those that kind of seek to resolve these issues within standard Lambda CDM with learning more about galaxy formation physics. Okay, so I once heard at a talk Carlos Frank say, if I ever hear anyone mention the missing satellites problem again, I'm going to walk out of the room. So Carlos, if you're here, now is the time to leave. And I think what Carlos meant is this is one of the most solved problems in astronomy, one might say. Oversolved. So if any of you have a solution to the missing satellites problem, and I didn't mention it today, I'm sorry. There are many solutions. I'm just going to kind of bracket it by I think different types of solutions. My thesis advisor, James Bullock, in 2000, used extended pressure theory that he tested against n-body simulations because back then we couldn't resolve Milky Way or M31 satellites. Remember, that's the missing satellites problem. It's that mass scale. But he showed that if you can bring the theory completely into line with observations if you assume that reionization prevents star formation in low mass halos. Basically, yeah, the reionization heats the gas and prevents it from collapsing into the, what that mass scale is, we don't know, but it does a lot to relieve this tension. 8 years later, his student, Eric Tollerud, corrected the M31 and Milky Way mass functions for selection for luminosity bias by the completeness limits of Sloan. And he also did this by assuming that the actual distribution of galaxies tracked a dark matter-only simulation via Lactea. And they actually found that there could be as many as almost 1,000 of these that are actually brighter than the previously least luminous satellite. And some people were calling this the found satellites problem. And in fact, we've found a lot of satellites, or at least, maybe some of them have been confirmed to be galaxies. So this is from the Dark Energy Survey, which has been finding smaller and smaller satellites, it seems, of course, in the southern hemisphere so far. And these things are interesting for a number of reasons, and they're tiny. I mean, some of them are so tiny, I think they had to pull up Evan Kirby's giant dwarf galaxy magnifying glass to find them. Okay, so my contribution to sort of this missing satellites problem, what's the smallest galaxy, was done with initially with the first round of FIRE simulations that feedback in realistic environments. And basically what I did is I simulated two sort of what we call M10s, 10 to the 10 solar masses in dark matter. Now these are analogs to classical dwarf spheroidals. They form about 1 million solar masses in stars, and then two ultrafaints. And what we found is not only did these isolated ultrafaints, a few times 10 to the 9, form galaxies, but the biggest subhalos of these objects formed ultrafaint satellites. And they sit here on the stellar mass-halo mass relation. All of these ultrafaints, what we called ultrafaints, are forming in dark matter halos, some even below 10 to the 9, but below a few times 10 to the 9, which was the mass scale I was interested in, trying to figure out, what's the lowest mass dark matter halo that can form a galaxy. So that was FIRE 1. Oh, yeah, actually, and I'm not the only one. So this was from Young-Wan's paper. I think she showed this here, and it shows that quite a few galaxy formation simulators are finding these ultrafaint satellites in dark matter halos below a few times 10 to the 9. But as you can see, there's absolutely no consensus on whether there's a cutoff, a sharp cutoff in galaxy formation, a halo mass that you can form a galaxy, or on really even the stellar mass halo mass relationship. So I think that this is something we should continue to pursue. Oh yeah, and and the resolution is different, and the way we're doing these things is different. But at some point, I think it would be an interesting or good sort of goal is to see if what do we think that cutoff is, and then we can start to decide. Okay, well, people are already doing this, but we can put more energy into finding these dark subhalos. Okay, so that's FIRE 1. FIRE 2 is the second version of FIRE. I guess I didn't need to say that. And just this is going to come into play later, but I'm going to just talk about a few changes. We updated the hydrosolver. It's now kind of a, so it's meshless finite mass, but it attempts to sort of bridge the gap between halo, grid-based and particle-based codes. We changed the way that we do supernova, the supernova ejecta. It's now solid angle weighted instead of mass weighted. This, I think, is going to be important to what I'm talking about later. It's somewhat numerical, but we now allow local ionizing radiation to propagate outside the local computational domain. We updated cooling tables, yields, recombination rates, and code optimization, so now we can go to high resolution. But before I talk about that, I'm going to talk about our standard Fire2 resolution M10s. So almost all of these have been run by Alex Fitz right here at UT. And he ran about 15, or most of the 15 here. And actually, it turns out only two of the 15 have ultra-faint satellites. They sit pretty much where the Fire 1 satellites were. But it got me thinking, or, I would expect more, I guess. Doesn't really prove anything. You have to compare apples to apples, right? So as it turns out, only at the time that I was looking into this, only one halo had been run with both Fire 1 physics and Fire 2 physics. And this is one of the M10s from my paper, and this is Alex's version with Fire 2. And yeah, it forms satellites in Fire 1 and not in Fire 2, but that's just one. So sample size of 1 is no good, but I'm absolutely going to blow your mind with my sample size of 2. So I went back and I reran M10Q, which is going to be a star in our story in just a few slides. I reran it with Fire 1 physics, and indeed, you can see them right there popping out. It does form satellites. So of the only two halos that have been run with Fire 1 and Fire 2, they both form ultra-faint satellites in Fire 1 and not in Fire 2. It's never the situation I guess you want to be in, but it's an opportunity to learn more about why these aren't forming. Okay, so this is that same stellar mass-halo mass relation. This is from my 2015 paper. I'm going to do something crazy now. I'm going to show you this really terrible figure that was never published. It's a resolution test, but it's going to illustrate a point, so don't take too many pictures. So if we zoom out now, we considered in that paper, we wanted to only consider galaxies to be resolved galaxies if they had a minimum stellar mass of a few times 10 to the 3. It also was a particle number count. That's not always the case, right? I mean, sometimes not everyone has chosen to do that, but low resolution makes strange bedfellows, I guess we'll say. But we didn't want to do that. But if you were to do that, if you look at it, you can see there's a whole big number of these things forming with 1, 2, 5, 6 star particles. And so it kind of makes you think, what if you had higher resolution than 250 solar mass baryonic particles, which is what Fire 1 and Fire 2 standard resolution is. So I did it, we did it. We're in the process of running a suite of 3 of these, but so far we have 1. This is dark matter only. So this is M10Q again, the hero I said would come back later. And at standard high res, we already have quite a high baryonic particle mass, or low baryonic particle mass. But we blasted that out of the water, and our new simulations are being run at 30 solar mass baryonic particles. It's, as I believe, the highest resolution cosmological simulation ever run to Z of 0. Not by much. The more I give this talk, the more I hear about Youngwon's got, what, 50? Alex Fitz has 40, but still 30 is still the champ. And when I was trying to decide what to call this, we already called everything else high res, so I just had to go with traditional standard astronomy naming convention. I'm going to call that super duper high res. And I think because it's the highest ever, might be why early this morning we got some attention from a very important figure. And only the best, only the best. And you might say he's got more important things to do on a day like today, but we'll take the attention. All press is good press. So if you get your baryonic particle mass so low, you run into certain challenges. So the way it's traditionally done in SPH simulations is you have a star particle. And that is, a single particle is viewed as a single stellar population with metallicity, mass inherited from its parent gas particle. And then you just say that represents a single stellar population with a Krupa IMF is what we use in fire. And then all of the feedback and everything is IMF averaged. However, if you start to get below 100 solar mass particles, you really, I mean, that makes no sense. What are you going to have, like a fraction of a type 2 supernova, a fraction of an O star? So instead, we had to start stochastically sampling the IMF. So now it's just a smaller number of baryonic particles have a discrete integer number of massive stars. This is completely on a tangent, but I do want to just illustrate how one of the cool things you can do with a simulation of this resolution. These are alpha over Fe to Fe over H for actual dwarf galaxies. In M31, you can see some are flat, some go down. You can learn a lot about the star formation timescale of these things. But if you try to do it in one of our standard high-res simulations, it's a little tricky to know what's going on. What's that clump there? Does it go up? Does it go down? But just look at the difference. I mean, now we have like a real actual track. We can see when the type 1a supernovas start to go off what it does. This is something I'm starting to look into, so I don't have any amazing results yet, but there's a lot of things I'm looking forward to doing with the simulation of this resolution. But back to the satellites, missing satellites problem, all that stuff. Okay, I already mentioned that there's no satellites in the high res, but what about the super duper high res? Okay, I don't know, I don't think so, but just to be sure, since I really wanted to be sure, I ran a halo finder, and Amiga Halo Finder told me, hey, there's a satellite there. I was jumping out of my chair. It's less than 10 to the 9 solar masses in dark matter, 720 solar masses stars, woohoo. But this is an important lesson. Do not believe everything you read in a halo catalog, because if you zoom in, there's not a single star that's actually associated with that dark matter halo. Alas, this is fake news. So even at super duper high res, we're not forming any of these satellites. So can I definitively say that now Fire 2 is, I mean, it does predict some ultrafaints, right? We have 2 that have ultrafaint satellites. But does it predict fewer than Fire 1? I think we need more simulations to be sure. There are a few possible things I thought of that might change it. I mentioned the long-range photoionization. I hope it's, we hope it's not the hydrosolver, but that was the single biggest effect that we saw on other properties. Could be anything. So my plan is to kind of take some of these dwarfs, turn these things off and on one by one, because if we can then go out and find these ultrafaint satellites of isolated local group dwarfs, then we'll know that, we'll be able to better constrain our simulations. Okay, Carlos can come back in. We're done with that. We're going to move on to the Cusp-Core Controversy. And since Mike BK is in the room, I better also mention Too Big to Fail. But they're Cusp-Core and Too Big to Fail. They're very similar. They're absolutely not the same, so I'll just describe them both. Cusp-Core, I kind of already mentioned. You have the rotation velocity. This is an NFW profile. This is a core. But Too Big to Fail is super interesting. So what Mike did is he took the Aquarius simulations, dark matter only, and he plotted rotation curves, and then he put the observed brightest Milky Way satellites, I mean not the 2 brightest, but the rest of them, on there, and he showed that actually there's a whole bunch of these satellite or subhalos in the dark matter only version that are too dense to host any single one of these actual satellites. And so the reason I say it's kind of an interesting way to think about it is a combo between Cusp-Core and missing satellites, is that you can alleviate this problem, maybe not solve it, but you can alleviate it if you start to decrease this dark matter density. But it also just might be that these things are missing, right? That's where the name comes from. They're too big to fail because they're not the ones you would expect would get shut down by reionization. But since the solutions to them are similar, I'm going to talk about decreasing that dark matter density as a way to alleviate these problems. Oh, and of course, so it's baryons to save the day, as it turns out. So Ponson and Governado in 2014 basically described, and this is a really useful chart, really helped me understand my thinking, how you go about decreasing dark matter density with baryons. So you have your dense star-forming gas, and your dark matter particle orbiting a certain distance. It feels a certain force of gravity. Supernova goes off, completely drives the gas from the center, evacuates that gas. It feels less gravitational pull since there's really nothing there, so it moves to a larger orbit. Eventually that gas cools back down, flows in, but by this point the dark matter particle is already farther away, so it feels a less force of gravity and it stays on it does not go back to its old orbit. Now, this sort of bursty star formation, these periods of this guy's breathing modes, it's been called, everything's got 3 names, but the gas goes out and back in, can slowly pull that dark matter out. turning a cusp into a core. I think Ariana DeCintio really kind of hit home the point, pointing out that, so this, it would be the slope here, so we have closer to 0 is a core, -1 being a cusp, and it really depends on the ratio of the stellar mass to the halo mass. You really have a peak formation, or peak efficiency here, where you have, down here, you don't have enough supernova energy, right? There's not enough, and up here, your halo's too big. And then Alex Fitz showed something even like also very interesting about this. He not only kind of reproduced the fact that you down here in the low stellar mass, you're not, so sorry, this is the central density in a hydro compared to the dark matter only, right? So this would be a cusp. Down here would be a core, and so you really only start to form cores up in the higher stellar mass range. But what he showed is that the extent of that core, how far out that core goes, is actually directly comparable. Where they start to break away is the half mass radius of the galaxy, which makes sense. Of course, everything makes sense when someone else figures it out for you. But here it is. So, oh yeah. So, what about this bursty star formation for a second? One of the things I wanted to look at with this simulation, this super duper high res, is what things do we think are converged aren't actually converged. And to be honest, I was hoping for way more. Turns out we're actually quite converged on most things, which is good for the simulations, but not so easy for me. But one of the things I wanted to consider is bursty star formation. Here we have, this star formation rate. It's very bursty. You get these blowouts here where you don't have any star formation again, and it blows out the gas. This is very common for this sort of mass scale. But if you think about it, what if you just have a low star formation rate? And if your particle mass is 250 solar masses, it's going to take you, if you're less than a 10 to the negative 6 solar mass per year, it's going to take you quite a long time to form a single star particle. So maybe these blowouts are resolution dependent. Well, in some ways they are. Yeah, you don't see them anymore, or maybe they're just much smaller. It takes much less time to form a single star particle. You still have what looks like a bursty star formation history, but the complete cessation of star formation, once again, I'm going to look further into this, but it could be resolution dependent. So in my efforts to look further into this, and actually this is something that was actually for another project, a paper by Ivana Skala, and she asked me to look into this after she saw my last slide. So what he did is we looked at, these are satellites of Latte, so this is a Milky Way mass halo run at also very high resolution with Fire 2 Andrew Wetzel's, and we looked at satellites. And I looked at the star formation. So we have fraction of stellar mass in bursts, where a burst is defined as you have your short star formation time scale and your long one. And if your star formation burst is greater than 1.5 times the average in the long, that's a burst. You count up all the stellar mass and you plot this fraction. So we can see low mass objects are always more bursty. That makes sense. But unfortunately, we see a resolution dependence. So the circles are the same. Same dwarfs, same satellites in different resolutions. So we have low resolution, high. And then the triangles are a different set, also in same satellites, different resolution. Now this time, red is low and blue is high. And you can see that indeed, lower resolution objects have higher burstiness. It is a resolution effect. Now that actually changes if you change this time scale. We're almost actually getting rid of it on a longer time scale. Don't yet know what to make of that. This is super preliminary, but I think it's something important to consider if you're concerned at all about the burstiness of your star formation. Oh, but even though, despite the fact that there may be some resolution dependence, we're still getting a core formed in our super duper high res. It actually forms a little bit more stellar mass, which is why I think it's a more pronounced core. But another cool thing you can just do is now we can trust the core down to a lower radius, right? There's the power criterion, which is the radius at which we can trust that we're resolved. It gets pushed down quite a bit. So, but we still form cores in about 10 to the 10 solar mass objects. Wow, I don't even have way more than 5 minutes, huh? Okay, might be getting out of here early. All right, so for the last 15 minutes or 5 minutes of my talk, I'm going to talk about, I'm actually going to move away from simulations. I've actually been working on a paper dealing with scaling relations versus this sort of diversity, since it's been not that long, but a long time since I mentioned this before. This is how I introduced it. You have all these different rotation curves of dwarf galaxies, and yet they all seem to follow these scaling relations. But more recently, this has kind of been put in a different way. And this new scaling relation, so people like Federico Lelli and Stacy McGaugh have been investigating a way, this relation that they say generalizes baryonic Tully-Fisher. So for those of you who haven't heard about it yet, I'm just going to spend a little time describing what's going on. So if you take the observed acceleration, so that's your rotation. Basically, it's just, you can assume everything goes on a circular orbit. It's v squared over r, centripetal acceleration. And you plot that on the y-axis as a function of the acceleration that you would expect just from the baryons alone. In this case, you add up the gas, and you add up the stars. And so you plot it against each other. They're completely independent, the axes. And you do this is a radial relation. That's why they call it, because they've been up in radius, and each point in the radius has a different value. So it's not like a single data point like baryonic Tully-Fisher. It's a whole radial relation. And if you do this for, like, I think the hundreds of galaxies in their Spark catalog, you see some interesting properties. So here at high acceleration, it follows this one-to-one line, right? And that makes sense. You have the observed acceleration completely tracking the baryonic acceleration. This is in the central baryon-dominated portion. That's where the acceleration is the highest. So we expect that. The strange thing, or I guess the thing that we need to worry about or explain, happens when you start to get to lower accelerations. Here, it's found that for on average, and for most of these galaxies, with a very low amount of scatter, the observed acceleration goes like the baryonic acceleration to the 1/2 power. You can see the observed acceleration overtakes what you would expect. You know, one way to describe this, well, that's where the dark matter is. But as it turns out, the best fit functional form that they quote is like a Mond-inspired or Mond-predicted function. So it also fits. And that has led these authors and others to say that this is now the fundamental relation, and Lambda CDM simulations must be able to match this, otherwise perhaps Mond. Or something else, don't know. Well, okay, so to answer the question now, okay, Lambda CDM simulations. Oh, yeah. Well, I didn't even hear that. That's all right, we have time. I have only 2 hands, though. Okay. All right. Is that better?
Yeah, that's better.
Okay. That's because I'm getting towards the end of my talk. I'm getting excited. Okay, so the short answer is that at least for these 2 sets of simulations, and possibly others that I haven't had a chance to see yet, they can completely reproduce these relations. So this is the MUGS simulations. I don't know that much about it, but there was some, criticism. Oh, the sample size isn't big enough. So then Ludlow et al. Came back with a much bigger sample size of the Eagle and Apostle simulations. And basically, simulations can match this relation. Some other authors then actually went into kind of an argument for why this must be the case. There's been actually quite a bit of work on this. And basically, I think the main argument is, well, there aren't that many dark matter halos for which we have observations. They're self-similar. And then the virial mass and the virial radius have tight scaling relations with baryons. So you can show this. But I wanted to handle it a different way. Getting back to the diversity of rotation curves. So what we did in this paper is we just took some analytic functions. So NFW profile, exponential profile, Hernquist. We made a fiducial L-star galaxy, that's the black line here. And we used, abundance matching to give it a baryonic mass, to just made these analytic galaxies. And then we just changed everything up like crazy. So all of these different lines are a different profile, a different baryonic mass. You change the virial mass, you change the virial radius, you change the galaxy scale radius. And just look at the wide range of rotation curves it creates. One of them I even threw a sine function into the density profile just to see how crazy we could get. And if you do this, and then all you do is you normalize that rotation curve to lie on baryonic Tully-Fisher, then you naturally have every single one of those rotation curves falling in with the observed scatter of this radial acceleration relation. You can see here where there's more room to place it. I mean, it doesn't really tell you, but these are the different values we used. We had 4 different values. We changed the concentration, the baryonic profile, the dark matter profile, the virial mass. And it's actually really hard to break this relation. So this doesn't necessarily go about it doesn't actually in any way explain baryonic Tilly-Fisher, but the point we wanted to make is let's not call this a new relation. I mean, in the paper, I thought I didn't have time to go into this, but in the paper we also show that the slope, the scatter, and even the acceleration scale, where it breaks away from the one-to-one line, are completely, you can derive them completely from baryonic Tilly-Fisher. So look forward to this paper. I don't have a schedule for when I'm going to complete it, but if I did, I would be way ahead of schedule. Okay, so conclusions. These are kind of more specific conclusions. The missing satellites problem has been solved a lot. That doesn't mean we shouldn't investigate it. It has many solutions, reionization, also feedback, selection effects. However, there's still no consensus amongst what is the minimum mass for halo formation, which I think is something we should at least predict. And so we're working towards that. And resolution has been the main issue. So to that end, we have a big arms race going for biggest and, well, yeah, I guess I'm saying we do, because then I can say that I'm winning. But as we get higher and higher resolution, this will be maybe an easier problem to answer. The new Fire 2 versions of simulations, they may form fewer satellites. I kind of suspect they do, but I'm not ready to say that for sure yet. We need more simulations. We need the same halos run with each. Burstiness can be resolution dependent and also timescale dependent on how you define it, so that's important to consider. Nonetheless, we can still form dark matter cores around this mass range. And then the radial acceleration relation can be easily satisfied for any galaxy that falls on baryonic Tilly-Fisher. Oh yeah, so if you're going to ask, well, I run simulations, right? The natural question is, did I check? I haven't checked yet. But the whole point was, you might as well ask me if my galaxies satisfy baryonic Tilly-Fisher. And that was the kind of point. We didn't want to look at the simulations because if they satisfy baryonic Tilly-Fisher, they're naturally going to satisfy this relation. I'll probably look someday, but we'll get back to you. Okay. And then I'd just like to end with broader conclusions throughout this project and writing this talk that I've thought of. We're not ready to throw out Lambda CDM. Not even close maybe, but I do think we should keep challenging it, looking for problems. And we should even explore alternative theories. Let's not be those people that were wrong, but let's also stick to our best theory that gets the most things right. But we can have both hats. And then finally, I was talking about this with Msun. As we get to higher and higher resolution, we're going to come to a point, or maybe we've already reached it, where we're getting close to simulations that are forming single star particles. And I don't think we're quite computationally ready to start doing that in a 10 to the 10 or a big cosmological simulation. So we need to start doing things like stochastic sampling, like forming POP3 stars, these sort of methods that bridge the gap and that are going to allow us to push to lower and lower, higher and higher resolution until we finally can start forming individual star particles in bigger zoom-in cosmological simulations. Thank you.
Okay, questions?
You started with the missing satellites problem, and then you compared your Fire 1 to Fire 2, and you said that the missing satellites that appeared in Fire 1 are missing in Fire 2. So could you clarify why it's not a good thing that they're missing in Fire 2 to solve the missing satellites problem?
Well, they are appearing in some Alex Fitz simulations, 2 of them. But so they are still a prediction of the simulation. So we didn't solve the problem that way. If we never formed any below the mass, I'd be done. But what I don't want to think is that I guess I'd like to be sure it's not a numerics thing. I'd like to think it was a physics thing. I guess simulators don't want to think there's some numerical thing that we did that's completely changed the prediction. But the satellites are still predicted, maybe not as robustly as I had initially thought upon running the Fire 1 simulations.
But the sense of it, that puzzles me is that you wanted initially to depress the number of observed satellites compared to the n-body predicted Hale solubles. And you said that nevertheless, that you attributed to reionization and feedback. But at the same time, you wanted to explain the number of satellites we do see. And then when you changed the algorithm, FAR 1 and FAR 2, and the ultra-faints went away, that worried you. So I don't really understand how we have an explanation that, we sought an explanation to depress the number of satellites. And then we were satisfied with FAR 1, and now we're puzzled by FAR 2.
Yeah, I mean, I
don't see why. What is the goal in saying we have enough satellites or too many satellites? Which is it?
Yeah, so I guess the goal for me would be to figure out what is it about the simulations that predicts them, what is it about the simulations that don't predict them, and that way, if we find them, we can better constrain the physics. I guess maybe I'm concerned because I don't know why this is happening. Not that it doesn't help, because it may not help us solve the problem, because I don't know. Just because it's FAR 2 doesn't mean it's more correct than FAR 1.
I get that it's a numerical issue now. But does this mean, are we in the realm of over suppressing missing satellites as a possibility?
It's a possibility, but I don't think we're doing that yet.
Other questions? Okay, there's not.
Okay. I don't want to take anyone else's question.
Okay, well,
nobody asking a question.
Well, I'm going to ask a question, and we'll see if that inspires anyone else. In the high-resolution simulation in the Dwarf Galaxy, you found that you still found the core and the density profile. Do you also find the similar trend that Alex Fitz found in that the suppression of the density profile roughly correlates with the? I put that figure up, but I haven't looked at that yet. But I will let you know. Yeah, it'd be really easy for me to check. And yes, I probably should have thought of that, but I didn't. Okay. I didn't yet. Cool.
Yeah, good question.
Okay, well, see, that inspired.
Yeah, but like I think about it.
I'm a runner.
This way we delay Paul.
Yes.
When you switched to the higher resolution, or switched to the higher resolution, and you saw the extreme burstiness went away. One of the things as an observer that I've kind of been noticing in the last couple of years is that we keep getting browbeaten over and over by assuming these incredibly contrived star formation histories for our galaxies, with the sort of caveat that in simulations they're incredibly bursty, and so what you're doing is obviously wrong. So now it looks like maybe some of that is going away, and so I was wondering if you wanted to sort of comment on that a little, if you would like.
Yeah, no, I mean, I don't know, because I don't know, I'm not an expert in the observations, but yeah, I think you should take a little bit of heart from knowing that maybe some of this. But the thing is, it depends on how you define burstiness. I can also define burstiness in a way that makes the resolution dependence go away. So that's why I said it was preliminary, is I haven't put a lot of thought into this, but it's absolutely true that there is some resolution dependence, whether that's going to have implications for observational predictables, or predictable observables. I don't know yet, but I think you could take a little heart.
Okay, we'll take one more question. All right, we're going to give it to Paul. Here you go.
So on the Cusp-Core issue, where the repeated expulsion of baryons followed by infall followed by expulsion seemed to solve the problem in a mass range that was sort of, I don't know, above 10 to the 10.
Yeah, like then to a few times 10 to the 11.
Okay, so here's the question. I think it is true that as you go to smaller mass objects, the ability to call upon repeated bursts breaks down. That I guess they're too disruptive, so you can't really expect to repeat that cycle enough to get that effect. Is there an observational problem at the the low mass end of that, where baryonic physics took care of the higher mass ones with this repeated ejection mechanism, but when you get to the low mass end, you've got observations to satisfy, you don't have a mechanism anymore. That's the question.
Maybe I'm not familiar with the observations, but just to be clear, our simulations don't form any cores in dark matter halos about 10 to the 9, but I don't think there's any definitive observational evidence.
Well, that's,
Definitive.
I think that's my question.
Yeah.
Between 10 to the 9 and 10 to the 10, it seems would be an interesting area to see if it really is baryonic physics. The baryonic mechanism may break down, and if there's still cores there.
Yeah, I mean, I think the only,
observation.
I don't-
Somebody could.
anyone know? But I think like, so SIDM simulations are forming cores in 10 to the 9. So I don't think there's any like sort of nail in the coffin sort of observations that would help. I mean, that would be great. That would be one thing that would be really good to distinguish between SIDM and CDM, or vanilla CDM.
Okay, with that, let's thank Dr. Wheeler one more time.